What is a logical statement? A declarative statement that is either true or false. Dogs are animals. I am asserting a fact, declarative, and it can be evaluated as true or false. The sentence, what is the time, is neither asserting a fact nor can be evaluated as true or false. Not a logical statement. You can combine statements by using logical connectives. This is the symbol for negation. It means not. So if we were to negate our previous example, we would get a statement that says, dogs are not animals. This V-shape means or. Simple statements can be compounded to make more complex ones. Combining our previous statement with a table is not an animal using an or gives us this compound statement. This is also known as a disjunction. Turn that V upside down and you get a pointy hat that means and, also known as the conjunction. This also combines two statements, but in a different way to the or that we'll get to very shortly. But before that, look at our statement about the table. This is just the statement, a table is an animal, but negated. This shows us two things. First, the same statement can be written in multiple ways. These two statements are equivalent. Second, we can put statements within statements. This is known as nesting, and you can get some pretty crazy and complex statements by repeatedly doing this. Now, what do these connectives actually do to our statements? First, to make things simpler, I'll represent logical statements with a capital letter, like P or Q. And just like the earlier statements, these could be true or false, T or F. The negation simply turns a true into a false and a false into a true. The or connective, or the disjunction, evaluates a compound statement as true if at least one of the statements is true. The and connective, or the conjunction, evaluates a compound statement as true if and only if both statements are true. These are called truth tables because they show the conditions necessary for a compound statement to be true. Why don't you pause the video here and try to work out the truth table for this statement? The best way to solve these types of problems is to create columns for intermediate steps and go step by step. You may have noticed in here that every combination of true and false for P and Q yielded false for the final statement. This is known as a contradiction. If every combination of true or false resulted in true, then the statement is known as a tautology. How could we more intuitively see that this statement would have been false for every combination of P and Q? To do this, we need to introduce a few very handy laws. First, the more intuitive ones. A statement negated twice is equivalent to just the statement. Note I am using the equal sign here, which isn't technically accurate in this context, but for the sake of brevity, assume that it means is equivalent to for this section. A disjunction or a conjunction of a statement with itself is equivalent to just the statement. Order doesn't matter with conjunctions or disjunctions. These statements are equivalent to each other. It also doesn't matter which conjunction or disjunction you evaluate first. These statements are equivalent. These ones require a bit more subtlety. In this one, statement Q is completely absorbed by P. Regardless of what Q is, these statements are true if and only if P is true. The distributive law. These work akin to how multiplication distributes over addition in arithmetics. The final ones in this section are really the holy grails of logic, De Morgan's laws. Although I am not a fan of rote memorization, a nice way to remember these two laws is that you quote-unquote distribute the negation and then flip the logical connective in the middle, or the reverse if going backwards. I will try to give more intuition on these once we introduce sets, but for now, you can show that these are equivalencies using truth tables. Try to draw out the truth table for the first equivalency yourself before I show you. Now let's go back to our earlier logical statement that we called a contradiction. Can you think of a way, using the laws that we just described, to transform the statement into an equivalent one, which makes it obvious that it is false no matter what? First, use the second De Morgan law to replace the left-hand side of the conjunction with its equivalent. Then use the commutative law and associative law to evaluate this conjunction first. And now we clearly see why this is a contradiction. The conjunction in the brackets here will never be true, since a statement and its negation can never both be true at the same time. And if this is always false, then the larger conjunction with not Q will also always be false. Now here's a more challenging problem. Pause and try to derive De Morgan's second law using the laws and rules we just described. If you would like a hint, then start by using the double negation law. So the idea is to first use the double negation law on P and Q, which gives us this. Now the key here is to see that this part inside the set of brackets is really just the right-hand side of the first De Morgan law, but with P as not P and Q as not Q. It might be clearer to define the laws using different letters, let's say A and B. Now, if you plug in not P into A and not Q into B here, you get exactly what we have over here after the double negation. So that means we can plug in the left-hand side of the first De Morgan law, giving us this. Using our rule of thumb from earlier, we flipped the OR connective into an and then quote-unquote undistributed the negation symbols. And finally, we can use the double negation law to get rid of the two outermost negation signs, leaving us with exactly what we wanted, the other side of the second De Morgan law. Now let's add the notion of variables to our logical statements. Sometimes it is helpful to write a statement about a particular kind of thing. We can say the statement P of X is a logical statement about X, which can be whatever we want it to be. For example, suppose the logical statement P of X stands for X is a prime number. Then you could plug in any natural number as X for it to be evaluated as being a prime or not. We can have as many variables as we want, and with this notation we separate them with commas. So this statement M of X, Y, and Z could represent the statement X is larger than Y but smaller than Z. Unlike the statement dogs are animals, where we can immediately say true or false, statements containing variables require the notion of a truth set to know when they are true. Before we define the truth set of a logical statement, we need to understand what a set is. A set A is just a collection of objects, and the simplest way to define them is within curly braces, separating each object or element with commas. So if we stick with numbers for now, this is a completely valid set containing the numbers 1, 2, and 3 as elements. But this won't get us that far. A better way to define a set is to spell out the criteria a potential element needs to meet to be a part of the set. So, if we wanted to define the set of even numbers, this is what it could look like. The straight line in between the X and the criteria is a way of saying such that, or given. So this notation reads, A is the set of all X such that X is an even number. The criteria is also known as the elementhood test for the set, since it decides which elements make the set or not. Take the set of all numbers greater than 10. We can check whether the number 15 is a member of the set using the elementhood test. This E-looking symbol here means is a member of, or is in. So we're asking if 15 is a member of this set, where all the elements are numbers greater than 10. And we've actually created a logical statement here, since this can be evaluated as true or false, and since 15 is indeed greater than 10, this statement is true. We can then generalize this by using a variable like y. We are now asking if an arbitrary number y is a member of the set of numbers greater than 10. Notice how x is just a sort of placeholder for y. We are given some y, and just like algebraic substitution, we use y as the variable in the elementhood test or the criteria. We call y a free variable, as it could take on any number we want, and is the object of the statement in question. We call x a bound variable because it's simply a placeholder to make expressing a set or statement more clear. It doesn't actually represent anything in and of itself. This means that it doesn't matter what we use as a bound variable. These statements are equivalent. So these statements are about y, and generally, this statement, where p of x is the elementhood test of the set, is the same thing as p of y. Thus, we can define the truth set of a statement p of x as the set of all x that pass the elementhood test of p of x. In other words, it is the set of all x that makes the statement p of x true. So the truth set of the statement x is an even number is the set of all even numbers, which goes on to infinity. If a statement is false for all x, then it can't possibly have anything in its truth set. Thus it gives us a set with nothing in it, called the empty or null set, denoted with an O with a line through it. This feels like an okay place to leave this first video, an introduction to sentential logic as a building block for eventually introducing first-order logic.